So good morning, everyone. Welcome back to the last week of COVID Spring 2020. It's so good to be with all of you in this interesting world in which we live. Let's look at Stokes' theorem. This is the beginning of section 17.7. So 17.7. So with the divergence, the curl, and surface integrals in hand, we're ready to present two of the crowning results of calculus. So we've done all the hard work, the heavy lifting, and so in this theorem, we're going to see Stokes' theorem. Sorry, in this section, we're going to see Stokes' theorem, and in the next and last theorem, before all of our paths diverge, we will study the divergence theorem. So here are the notes. So Stokes' theorem is a 3D version of the circulation form of Green's theorem. So one of the things that you probably recall is that there were actually two versions of Green's theorem. Better switch to a green pen. Green's theorem. And so we had the circulation form and the flux form. And so this is the circulation form of Green's theorem. And you'll remember that this argument in the middle of Green's theorem was the 2D curl. So in Stokes' theorem, the plane region that was in Green's theorem becomes an oriented surface. Remember, oriented surface means not a what? Not nice, Enrique. Oriented surface means not a what?
That funky loop that has one side.
Yeah, exactly. Not a Mobius strip.
Yeah, that's the one.
I think it's got the double dots there. Like umlaut. Is that from German? Can anybody help me on my
Looks like a surprise face.
Yeah, nice. Say that again, Croy.
Kind of looks German to me. Yeah.
I think it's German, but yeah.
It is.
Okay. Thanks, Robert. All right. So anyway, so the plane region R in Green's theorem becomes an oriented surface, aka not a Mobius strip. And so the circulation integral in Green's theorem remains a circulation integral, but now over the simple, closed, piecewise, smooth, oriented curve C that forms the boundary of S. The double integral of the curl in Green's theorem becomes a surface integral of the three-dimensional curl. So if you compare the two theorems, you'll see that the circulation part is identical. And then the right-hand part, where up above we had that 2D curl, now below you get the full-on 3D curl. So they're very much directly paralleling it. So if you were tracking Green's theorem, then Stokes' theorem is just the 3D version. Questions about that?
3D curl.
So it's talking at, so remember the curl is giving us some sort of a measure of the vector field is rotating at a point.
Is that kind of like eddy currents where you have like a three-dimensional thing moving around? Oops.
Yeah, yes, except for like an eddy would actually be over surface. This is just like right at a single point. Like how much eddying is happening at a point.
Thank you.
And then what we care about in all that is what's the normal component to the surface. Like, so how much of that rotation that's happening is normal to the surface? Because the rotation is happening in the field, that's everywhere. But it doesn't all impact the circulation. All right. So we should pony up and check out this manipulate here. So there's the two halves of of Stokes' theorem. So you have this left-hand side, and on the left-hand side, you're talking about the circulation around the outside of the surface. Sorry, the outside of the curve. Yeah, Shetland pony, that's fine. So here, going around the outside, and we could ask ourselves, what's the circulation if we go around the outside path? And then Stokes theorem says, well, what we could do is we could look at the circulation, not the circulation, the curl all across this surface. And so the curl is telling us, you know, how fast is the little wheel spinning at any given point. And if we added up all of those little spinninesses across the whole thing, then that would give us, so that'd be the sum. That's why you have this double integral of the curl. That would give us the total circulation around the boundary. So this is the right-hand side right here. So circulation around the outside would be equal to the sum of the spinniness, if you will, of the across the whole surface. And one thing to note is that this picture is focusing in on the normal component. Let me see if I can find it. So notice we're asking ourselves always the flux that's perpendicular to the surface. So you guys spinning around the Shetland pony? Is that what you guys are doing? Oh no, that's a question about this. Okay, so let me see if I can answer that. So as we, let's see if it goes faster anywhere. So right at the origin, notice that it's barely spinning at all. You can just barely see the thing moving, but let's see if we can find a place where it maxes out. Oh, that's not very helpful. Come on. There's a little faster spot. Here, notice that that quantity is negative, and so the wheel is spinning clockwise. I think if we come up here, it's spinning pretty fast, right? That quantity is bigger than 2, and it's positive, so it's spinning counterclockwise. Did that answer your questions, Croy and Enrique, from the chat? Does that help? Cool, cool. All right, any other questions about the animation? Very good. All right. Okay. So again, the point is that the circulation around the boundary is equal to, see if we can get some, is equal to the net curl across the surface. We say the net curl, that curl is talking about the spin of the paddle, and that indicates the curl at the point. So the speed of the spinning is reflective of the curl at the point, and counterclockwise would be positive curl, Willie's dotted with the N, and clockwise would be negative curl dot N. Curl is a vector, you dot it with the N to turn it into a scalar. Questions? Keep going. Very good. All right, so Stokes theorem involves an oriented curve C and an oriented curve surface S on which there are 2 unit normal vectors at every point. So Make sure this is clear what's going on. So there's always an up arrow, and there's also a downwards normal. There's two possible orientations. So these orientations must be consistent, and then the normal vectors must be chosen correctly. Here, I think there's a typo here. Here, the right-hand rule relates the orientations of S and C and determines the choice of the normal vectors. And we all remember the right-hand rule from previous stuff. So a common situation occurs when C has a counterclockwise rotation. That's the one that we were just talking about earlier. When viewed from above, and then the vectors normal to S are going to point upward. So you're going to find that at some points in your homework, at some points when you're working on this, you just need to check your orientation and make sure the orientation is right. What do you do if the orientation is backward? How's that going to impact your results?
It'll be negative.
Wouldn't we just have negative?
It'll be negative, exactly. So it's not hard. It's not hard. It's not hard to check. It's not hard to fix. It's just more of one of those issues where you have to remember to do it. And I think I've got that shown in all of our examples in this section today and tomorrow. Nice. Okay, let's keep going. So here's Stokes' theorem. Before we had it, just the short version, here it is kind of in all of its glory. So Stokes' theorem, let S be an oriented surface in R3 with a piecewise smooth closed boundary C whose orientation is consistent with that of S. Assume that F equals FGH is a vector field whose components have continuous first partial derivatives on S. Then the circulation about C of F dot dr is equal to the surface integral of the curl dot n ds. And maybe you're hearing me say this, but not catching it. Remember that del cross F is equal to the curl of F. And you'll see both of these notations used in the handout. So the meaning of Stokes' theorem is much the same as for the circulation form of Green's theorem. Under the proper conditions, the accumulated rotation of the vector field over the surface S, as given by the normal component of the curl, equals the net circulation on the boundary of S. Questions about the definition, or are you ready for an example?
Example.
Yay for examples. All right. So let me show you where we're going with this example before I switch over to the .cam and actually start working through it. So notice that you have this Stokes theorem, and it's got the two sides. So here's your left-hand side, and here's your right-hand side. And so what we're going to do is we're going to work through this example one below, and we're going to find the circulation using the left-hand side formula. And then we're going to work through the exact same thing, but now using the right-hand side formula. And we hope that at the end of the day, we find the same number at the other end, right? So we're just trying to kind of verify how this works. Later on, when you're doing your homework or when you're using this beyond this class, sometimes you'll be given a line integral situation and you'll switch it over to a double integral situation. Other times you might start with a double integral and write it as a line integral. You have the freedom to go both ways. But the point of this first example is just to see how these two things come together. Ready?
Yep.
Very good. All right. So the question is, let C be the intersection of the paraboloid Z equals 4 minus x squared minus y squared and the xy plane. We want to verify Stokes' theorem for the vector field F equals 2z, 3x, 5y if the parabola is oriented upward. And so here you have the picture. Here's that paraboloid. Your C is the boundary around the base. That's the C. And so when we work this left-hand side part to start with, we're going to be finding the circulation to go around this path. And then when we do the right-hand side across the surface, we're going to be finding the double integral of all that curl across this paraboloid. So let's do it. It's not super hard, but it's also a little bit lengthy. So just hold on. All right, so we want to evaluate the circulation about the curve C, which we've already talked about. Here's our C. And across this field F equal to 2z comma 3x comma 5y. Our process is going to be the same as the one we've done in the past. So what's step one?
Parameterize.
Parameterize. So, and the question is, what are we trying to parameterize here? Because there's multiple things going on. So what is it we're parameterizing?
The base.
Yeah, the C. Not, so this thing right here, this is our S, the surface, but we're trying to parameterize the line C. So it's a curve, so we only need one parameter, R of t. And so how do you parameterize this?
Two cosine t, two sine t, and 0.
2 cosine t, 2 sine t, because it's a circle. And then we have a 0 because we want the circle to live on the xy plane. And this would be for t's between 0 and 2 pi. All right, so then what's step 2?
Parameterize s.
We'll come back to S.
Okay.
So that'll be a step 1, part 2, or part 2, step 1, or something like that. But just in our normal evaluation of a line integral, what do we do after we find our parameterization?
Find our
Our dr, exactly. Find dr. So this one's nice. -2 sine t, 2 cosine t, derivative of 0 is still pretty close to 0. So that's looking pretty good. And so then step 3 is to substitute and integrate.
Seem you miss dt, right?
Thank you. Thanks, Vu. We want to substitute and integrate. And so our circulation will be the integral from 0 to 2 pi of, so now we need to substitute into our F. So 2z is going to become what?
0.
0. 3x.
-6 sine t.
Remember, you're going with your R.
6 cosine t.
So this will be 6 cosine. Yep. I've gotten that wrong so many times, just like looking at the wrong place. And then 5y would be 10 sine. So then we're going to dot this with 2 cosine t. Oh, there, I just did it. It's weird. My wife is homeschooling outside my Corona Cabana office, and she's reading aloud to my son, and she's actually reading aloud as we speak about the Martin Luther King Jr. in Birmingham jail.
Yeah, that's a pretty powerful letter.
It is, but I'm like, I think it just is coincidental that she's this place in the curriculum. You can't get much better timing than that. All right. So if you dot all that stuff, what do you get?
12 cosine squared.
12 cosine squared? Nice. Okay. And then we have to use our half angle identity and we evaluate, and that part is just a whole bunch of writing, right? So can we just jump straight to the number there? Is that okay? Because I don't think anybody has questions about how to evaluate this thing. So are you guys okay with me just going straight to this being 12 pi?
Yeah.
Okay. All right, I'm enjoying all of you guys' collective wisdom on chat, so thank you all for that. So here, switching back for a moment to the notes, what have we done so far? We went through Stokes Theorem, and we just said, hey, the left-hand side here, this would be 12 pi. And so now we're going to go back to the same question, and we're going to work through the surface integral side and see whether we get 12 pi on that side as well. Very good. It appears that Lord of the Rings is at least part of the theme for today. Okay, so let's go back.
It should be part of our theme every day.
It should.
Agreed.
It should. Okay, so same question, same field, 2z, comma 3x, comma 5y, but now we're going to focus in on our surface, 4 minus x squared minus y squared, and we care about the part that is above the xy plane, or on or above the xy plane. And we're going to try to evaluate the surface integral of the curl of f dotted with n ds. So what's step, went out of focus. What's step 1?
Find a 3D curl.
Oh my gosh, you guys are crazy. Before we find the 3D curl, we need
Parameterize?
to parameterize.
Parameterize,
Yeah.
yeah.
So I'm going to just try to keep to the same 3 steps, and then we'll add that 3D curl part to that step 3. So parameterize. This is a surface, so how many parameters are we going to have?
3 or 2?
2. It's a surface. So a line, something that's linear, like a line integral, will have 1 parameter. If it's a surface, it would have two parameters. So we'll have r of u cross v, and you'll discover later on in this section that there's some shortcuts for these types of functions, but we'll do it the long way here. So what's our x going to be?
U,
X is going to be u,
V.
v. This is like your name. This is like your favorite, right? Except for, should we do vu just for you?
Yeah.
Nice. So, oh, no end bracket yet. So we've got backwards vu for our parameters, and then what's our z?
4 minus U square minus Y square.
Yeah, minus v squared. Yeah,
V square.
cool. And this will be on which u's and v's?
U is equal to, wait, no.
So this is where you got to be a little bit careful. So this would be where we want the u's and v's that will keep us in this region, that are basically above this disk. And so maybe we could say on u squared plus v squared less than or equal to 4. Does that make sense to people? Because this would be the disk.
Yep.
Okay. So we parameterized. So second, we need to find our differential element. And so in this case, our differential element is ds with an arrow over it, which would be the same thing as n ds. These are all like big S's. And the formula for nds is Ru cross Rv d dA, like du dv. So there's like 3 different formulas for the same thing right here. The easiest one being the most concise. The second one being the one that's sort of easiest to figure out what's going on. So this is always the normal component, trying to find the normal component of that little surface area bit. And the last one is the part that gives you the formula to actually calculate it out. So like 3 different versions of the same thing. So we need to find Ru. So what's Ru? Or Ru? Anyway, what's Ru?
Are you okay?
I'm struggling actually. Thanks for asking.
That would be 1, 0, negative 2u.
Negative 2u. Okay. And then RV would be 0, 1. The ones and commas sometimes look a little bit too similar. Minus 2v. And then, so pro tip, when you have to find a cross product, if you actually write the cross product out, then you're stuck having to do that whole determinant. You're going to do that whole determinant, and you got to have your i's, j's, and k's, and it's a lot of writing. But if you have your Ru and your Rv written down, notationally, you can save yourself a little bit by writing Ru cross Rv directly below it. And then you have everything you need to calculate the cross product immediately above. And so let's just use these things and go straight to our answer. So we know that our first component is going to come when we cover up that first column. 0 minus minus looks like 2u. And then we go to the cover up the second column, minus 2v, but it's the middle part, so it's negative again. So you're going to get 2v, and then cover up the last part, and you'll just get 1. Questions about where Ru cross Rv came from? This will be a dA. Now, we need to find that thing that Damon mentioned a while back next. So what was it that you said we needed, Damon?
A 3D curl.
We need that curl. So step 3 is going to be to sub and integrate. But before we can do that, we need to find the curl. So remember that the curl of f is the del operator cross f. So here I actually am going to write out the whole thing. I've got 2z, 3x. If you're trying to figure out how to space things, you would probably discover that it's easiest if you do the third row first, and then immediately above that, you can do your partials. And then immediately above that, you can do your I, J, and K. Tends to keep the columns aligned. If you start with your I's, J's, and K's, then usually things don't end up aligning the way you want them to. All right, so to find the first component, partial with respect to y, looks like we've got 5. 0, minus 2, but it's minus minus, so there's positive. And then 3. Okay, on my curl finding. So we can put this together and we get that our surface integral of the curl of f dot n ds, big S, will be equal to the double integral of 5 to 3 dotted with RU cross RV. I think that's, which was which?
That's the 2u, 2v, and 1, right?
Yeah, 2u, 2v, 1. And this is going to be dA still. We got time wise, we're getting close.
Wasn't that negative 2v?
Yeah.
Let me go back because I'm surprised on the sign.
I thought it was positive.
So that would come from the middle term. So it would be 1 times negative 2v, which would be negative 2v, but then because it's the middle term, we need to change the sign. So you're correct that I wrote a negative 2v, but it should have been positive. Right there.
Okay.
Thank you for helping me catch that. Appreciate it. All right. And then I don't want to mess around with my limits of integration yet at this point, so I'm just going to write, this is for when u squared plus v squared is less than or equal to 4 at this stage. So from there we can calculate our dot product. So 10u plus 4v plus 3 dA u squared plus v squared less than or equal to 4. So if we were to try to evaluate this thing directly, we should switch to which coordinate system?
Cylindrical.
It's just a double integral, so
Oh, yeah.
so we just need polar coordinates. But polar coordinates are, I mean, that's fine, and we can do that. But what I simply want to point out is that we could actually split this up into 3 different integrals, right? This is the double integral of the 10 u's plus the double integral of the 4 v's plus the double integral of the 3's. Does that make sense? There's sort of like 3 different parts. And if you think about this region, so here's 2, 2, u, v. So if you focus in on the u's, notice that u is going to be positive in that circle and in this circle, and negative in both of those two. And there's, because of this integrand and because of this region, there's the same amount of positive and the same amount of negative. So what are you going to get when you integrate all of that stuff? Since there's the same amount of plus and minus.
0.
You're going to get 0 out. And if you focus in on the v's, v is going to be plus in quadrants 1 and 2 and negative in quadrants 3 and 4. The integrand is just v, and so you're going to get the same amount of positive and negative contribution. So what's that 4 going to contribute to the sum? Just, again, happy
0.
Happy 0. So the only part that's actually going to impact the final result is just the 3. And so you have a double integral across a circle of 3. And so your final answer is going to equal 3 times the area of the circle. And what's the radius of this circle?
2.
2. So the area would be pi r squared, or pi times 2 squared, or 3 times 2 squared times pi, or shockingly enough, 12 pi. So whether you evaluate the circulation using using the double integral version here, or using the line integral that we did earlier, either way, you're going to end up with 12 pi, the same answer. And we have officially verified Stokes theorem works for this particular example. So there's lots going on in this world. There's a lot of stuff outside of our control. Kind of echoing some of the things that have been said before, I just encourage you to have grace with each other, grace with yourselves. Fight for justice. Fight for justice. And in the midst of all of this, I'm stoked to be able to spend this time with you, and I'm stoked that we will get to continue this conversation tomorrow. So have a wonderful day, everyone. Feel free to hang on the line if you have questions or want to chat about stuff, and I will see all of you tomorrow. Take care.